Okay, in this video we want to discuss just a little bit about something called real quadratic forms. Okay, we'll just be referring to them as quadratic forms after a while. We'll assume that they're real. But for the original definition here, a real quadratic form in n variables, say x sub 1, x sub 2, out through x sub n, is a polynomial in these variables with real coefficients, so that's where the real part comes in, such that every term is of degree 2. Okay, so every term has just degree 2. So that means if you were to write it without exponential notation, that means the non-coefficient part, the variable part, would be the product of two of the variables, not necessarily distinct. Okay, so let's take a look at this. Okay, example 1. I've got 3 times x1 squared plus 8, x1, x2 plus x2 squared. This is a real quadratic form in the variables x sub 1 and x sub 2. Okay, you can see the degree of each term is what? 2. Okay, and the coefficients in front of these are indeed real numbers. So that's a real quadratic form. Okay, our goal to make a change of variables, okay, in a real quadratic form, so that the resulting new quadratic form has every term being a constant multiple, a real constant multiple, I should say, of the square of a variable, okay? So we want to rewrite things like this so that we've only got squares of variables here, okay? So terms like this, x1, x2, would not be acceptable, okay? But something like this, x squared plus 4y squared, has the form we wish because every term is a real multiple of a squared variable, okay? So there's no xy term here. That would ruin it for us, okay? So this is just something we want to do here, okay? There I already noted that the first one wouldn't be appropriate here because of that x1, x2 term. I want you to observe just kind of quickly here the following. I guess I wrote it twice. But if I've got this, okay, I've actually got a general quadratic form in x1 and x2, okay? For convenience, I actually wrote the coefficient on x1, x2 as 2 times a certain number, which I'm going to call a sub 1, 2. Okay? And then the coefficient in front of x squared is a sub 2, 2. The coefficient in front of x1 squared is a sub 1, 1. Okay, I just want you to notice here that this is actually equal to the following product. It's, if I imagine this column vector x1, x2, and imagine on the opposite side here, it's transpose. And then I've got this matrix here in between them, which is A11, A12. This would usually be what? A21, but I'm going to have it be a symmetric matrix, okay? So that means it's going to be the same as A12. And then I've got that last term, A sub 2, 2. Now, if you actually take the product of these, notice what you get here. You get x1, x2 as a row vector, and times the following column vector, a sub 1, 1, x1 plus a sub 1, 2, x2, and then what? A sub 1, 2, x1 plus a sub 2, 2, x2, and when you multiply those, you get exactly what I have above here. So it works here. So you see how I've written this, you know, this could be generalized. This is a general quadratic form, what they would look like in two variables, right? Any quadratic form in two variables could be written this way. Alrighty? Alright, so a vector transpose times a real symmetric matrix times the vector. Okay, let's try it for 3 variables here. Okay, I claim this will work. Okay, a sub 1, 1, a sub 1, 2, a sub 1, 3, a sub 1, 2, again, this is going to be symmetric. A sub 2, 2, a sub 2, 3, a sub 1, 3, symmetry, right? A sub 2, 3, a sub 3, 3, x1, x2, x3. So there I've got it, right? Okay. Now, when you just take the product here, see what you do? Okay, take the product of the matrix and the vector, we get this vector here. Okay. Then I will multiply it by the transpose of that column vector. In other words, this row vector x1, x2, x3, and we get the following. a1, x sub 1 squared, 2, a sub 1, 2, x sub 1, x sub 2, 2, a sub 1, 3, x sub 1, x sub 3, a sub 2, 2x squared, 2 times a sub 2, x2, x3, plus a sub 3, 3, x sub 3 squared. Okay? Notice that any, quadratic form in 3 variables could be written this way, right? All right, this is just completely general here. In fact, you can see here, just generalizing this, that every quadratic form in no matter how many variables you're dealing with can always be written this way, with x bar transpose times a times x bar, where x bar is the column vector consisting of your variables in some order, and A is a real symmetric matrix, okay? All right, so you can always think of it this way. And this is going to help us solve our problem. Remember how we want to rewrite this with a change of variables so that all our terms involve just squares of variables instead of cross multiplication, okay? So like products of different variables. Okay, let's return to example 1, and let me just show you how we could do this. Okay, the first example, this was our quadratic form. 3x1 squared plus 8x1x2 plus x squared, and I claim it can be written this way. x1, x2 is a row vector times 3, 4, 4, 1 times the column vector x1, x2. Notice that these are 4s. Why are these 4s? Because as a product, x1, x2 times 4 is actually going to appear twice in our summation, giving us what? The 8x1, x2, right? Okay, you can see that up here, right? Remember, when you multiply these, notice when the variables are different, I'm getting a factor of 2 in front. Okay, I've got to compensate for that by taking halvesies, dividing by 2, to get these elements here. Okay, and the same thing with everything on the off diagonal. Already? All right, in example 2, okay, we said this was an acceptable form, right? Because there's no xy term. It's only dealing with squares of variables. Okay, x squared plus 4y squared, that was our second example, could be written this way. xy is a row vector times 1, 0, 0, 4. xy is a column vector. Okay, notice why this is acceptable. Okay, this is acceptable because what? This matrix A that we're using for this one is actually what? Better written as D. It's a what? Real diagonal matrix, right? It's a real diagonal matrix instead of just a general symmetric matrix. Of course, all diagonal matrices are symmetric, but this is very specific. All the elements off the main diagonal are 0, and that's precisely what we're looking at for now, right? Okay, does that make sense? So that way we get no more of these, what? I always get coefficients of 0 when I'm multiplying different variables together. That would correspond to what? Having zeros on off the main diagonal. Okay? So we're really looking to diagonalize the matrix. Now, you guys remember, we did this last time, from the spectral theorem, every real symmetric matrix has a real diagonal form. Okay? And we know how to do that, and we'll do that here in a second with an example. Thus, if a quadratic form is given by x bar transpose A x bar, where A is real symmetric, then A can be written this way. P D P transpose, okay, remember that? And the quadratic form can be written this way, okay? That would be what? X transpose P, D, D transpose X bar. And if I let P transpose times X bar be Y bar, okay? So I'm going to reimagine giving this, I'll call that Y1 or Y2 or something. So I'm making a change of variables here. Then what happens here? What would Y transpose be? Y transpose would be this fellow right here. Oop, I forgot a little bar on top of that guy. Okay, that would be what? X bar transpose P, D, P transpose X bar. In other words, it would be Y bar transpose D Y bar. And that would be a quadratic form in the form that we want. Every term is a real multiple of a squared variable, okay? Because D is diagonal. So that's it. Okay, now let's do a concrete example. Okay? Now I gave a name to the diagonal form. I called it f of x1, x2, but I didn't do example 1 or anything, but I created one that was kind of neat here. Consider the following real diagonal form. 3x1 squared plus 2x1, x2 plus 3x squared. I'm calling that f of x1 and x2. So it is indeed a real quadratic form. Okay, now notice there is a 2 in the middle there. So that if we were going to write this as a matrix product, we would have what? x1, x2 row, right, vector, 3, 1, 1, 3 times what? x1, x2 is a column vector. Okay, that's half of this, right? Okay, that's half of the 2 right there. That's where it came from. We took half of those. All right, I want to find P such that what? A equals what? P, D, P transpose. We can do that, right? Okay. Orthogonalization here. We can do that in the case of what? A real symmetric matrix. Okay? Let's look for eigenvalues first. So I'm going to take the determinant of x times I minus a, and I would get that right there. Okay, so computing the determinant, it turns out to be easy. We get x squared minus 6x plus 8. So that actually factors. Okay, so this shouldn't be too ugly here. It factors as x minus 2 times x minus 4. Okay, so I've got 2 eigenvalues. I'll call them lambda 1 is 2 and lambda 2 is 4. Okay, now let's look at, let's take the first eigenvalue 2, that is, and find a corresponding eigenvector. Okay, so if I just substitute x equals 2, x equals lambda 1, which is 2 in there, I would get 2 minus 1, minus 3, minus 1, minus 1, 2 minus 3. That's set to 0, right? Okay, now this row reduces and everything to 1, 1, 0, and the zeros on the bottom. If I called those v1 and v2 the components of my eigenvector, then you could see any scalar multiple of this vector 1, negative 1, which I'm calling v1, would be appropriate, an eigenvector corresponding to the eigenvalue lambda 1 equals 2. Now I put the little hat on there. That indicates that it's a unit vector. So what I did was take this fellow and do what with it? Divide it by its own magnitude. We're going to need that to form our p. Okay, our p above. All right, let's look at lambda 2 equals 4. Again, going back up there, we would have what? Lambda minus 3, negative 1, right? Which is 4 minus 3, negative 1, 0. Negative 1, 4 minus 3, 0. This row-reduced echelon form goes 1, negative 1, 0. Okay? And you can see that an eigenvector corresponding to that would be what? 1, 1. Okay? And a unit eigenvector would be what? 1 over the square root of 2, 1 over the square root of 2. Okay? Now I'm going to throw this in here, right? These should be orthogonal. It might be just a quick check mentally. These two should be orthogonal, right? Because they're eigenvectors corresponding to eigenvalues of a real symmetric matrix that have what? Different eigenvalues, right? So these should be orthogonal. That means v hat and v2 hat are orthonormal, meaning they're also unit vectors here. So we can form our p in this way, right? So I've got I've got v1 hat here, right? And then in the second column, I've got v2 hat. Okay, the p transpose is actually the inverse of p, but this is what p transpose would be, right? It just interchanges rows of columns, and I get this. You could check if you wanted to. You could take the product of these two as a check, but that would really come from the fact that these guys are orthogonal up here, and in fact orthonormal. I should say the product of these two is in fact I, proving that P transpose is P inverse. Anyways, our D corresponding to this particular order on the eigenvectors. This was what? An eigenvector corresponding to lambda equals 2. So that's going to come first in our diagonal. And the second one corresponded to lambda equals 4. So our D is going to be 2, 0, 0, 4. Okay? Now, A should be what? P, D, P transpose. Okay? So that's just what we have here. All right? Now, let's go back to our actual quadratic form. Remember our quadratic form? All this ugly stuff is just A. To get the quadratic form, what did I do? I multiplied A on the left by the row vector x1, x2, and on the right by the column vector x1, x2. So now I've stuck in this new form for A, and we've got this. And now what I'm going to do is just gather the product this way, these two, and I'm going to give that the new name. That's the y1, y2, okay, or my y vector. Okay, so that would be the product. Reading across, 1 over the square root of 2, negative 1 over the square root of 2, 1 over square root of 2, 1 over square root of 2 times x1, x2. Take that product and you've got this. So that means y1 is x1 minus x2 all over the square root of 2, while y2 is x1 plus x2 all over the square root of 2. Did I write 3 there? What did I do? Okay, that should be a 2. Okay. And then if you do that, of course, the transpose of that would be this stuff over here. Okay, so I'm not going to write that again. So that would be what? y1, y2 as a row vector. Then I've got 2, 0, 0, 4. Okay, times 1, 2. And that ends up being what? 2y1 squared plus 4y2 squared. And I could give that a new name, g of y1 and y2. Okay? All right? So the point is that my original quadratic form can be written as what? In the form I like, with sums of squares on the variables only, if I use what? That change of variables. Okay? Now, you should be equipped by looking at this example for questions in the book along these lines. Okay? All right. Hope you understood.